So the next intermolecular attraction are dipole-dipole attractions, and this is with all polar compounds. So if you have a polar compound, you have a permanent dipole. Basically, you have a magnet. So like hydrogen chloride, the bond dipole is permanently there, meaning this molecule is always permanently a little bit more negative on one side than it is on the other, because the chlorine has a large electronegativity. So basically I have this set up all the time, and so the attraction between the molecules, between the negative end and the positive end of the hydrogen chloride molecules, is the dipole-dipole attraction. So remember, looking at the forces between the molecules, just like when we have the attraction between north and south magnets. So when we have a polar molecule, we have that attraction permanently there. And you can see that they arrange themselves so that the positive end is attracted to the negative end as the molecules are facing each other. So what does this mean about something like boiling point? Remember, the harder it is to pull apart the molecules, the stronger the attraction, the more energy it's going to take to do something like boil a liquid. So see if you can answer some of these questions about boiling points and then the differences between something like carbon monoxide and nitrogen. The third type of intermolecular force is hydrogen bonding, and basically it's a very strong type of dipole attraction. It occurs in polar compounds that contain hydrogen fluorine, hydrogen oxygen, hydrogen nitrogen bonds. They have to be part of the compound. So like in water, I have a hydrogen oxygen bond, and I have a dipole just like I had it for hydrogen chloride. However, because the electronegativity is very high for oxygen, nitrogen, and fluorine, this dipole is quite large, meaning I have quite a strong magnet. And so when the hydrogen of one water molecule is beside the oxygen of another water molecule, this is quite a strong attraction. So ammonia has the same kind of attraction. The area where it has the negative end, the electronegative end, which is the nitrogen or the oxygen, is attracted to the hydrogen of a neighboring molecule. So this is what we call hydrogen bonding, a very strong type of dipole-dipole. And there are really quite special properties of hydrogen bonding. It's amazing. We know that water has this arrangement, and you can see this is the arrangement of water in the solid state, in ice. So the arrangement of this of the hydrogen and the oxygen of neighboring molecules gives rise to that snowflake shape. You can see the hexagon kind of being created because I have all of these lined up. And if you can see right here, there's giant spaces inside this ice formation. And so that those giant spaces that form because the water molecules are forming in this hexagonal shape is creating a greater volume in the solid state. So water is very unusual, and so when it does that, it needs to expand. So when winter comes, the metal pipes that contain the water, they are just, if they're full to capacity during the fall and warmer months, then that water needs to expand, and the only way it goes is out. So imagine this hydrogen bonding force is really breaking the pipes, these steel pipes or these metal pipes. That's an incredible force. And this also explains our DNA system. It is amazing because the base pairs in DNA have nitrogen and hydrogen and oxygen, and they have these polar bonds here, and they're attracted to the other atoms in the neighboring molecules and create this hydrogen bonding force. And it is because of the hydrogen bonding force between the base pairs that form this double helix of the DNA molecule. And the really amazing thing is that the hydrogen bonding force is strong enough to keep your DNA intact, but also weak enough so when you need to replicate the DNA, it allows that bond to break without that much effort for replication. And as you may know, the replication for cells is like 99.9% accurate. So thinking about this, the hydrogen bonding forces versus the other forces, and then how this affects compounds, try to answer these few questions.